Hey guys, Mr. T here. This is another video on trig. This is the last sort of directly right angle triangles trick that you need to do, I think. And that involves problem solving with trigonometry. So we always link your maths back to real world applications of it. And this is that for trigonometry. So right angle trig can be used for real life problem solving, especially if you're a tradie or an architect, that sort of thing. Not architects are designers, maybe engineers. So all you need to do is find the right angle in your situation. Then you need to use the appropriate trigonometric ratio, which you've been learning about in isolated exercises that just involve non-real life applications, and use that trigonometric ratio, sine, cosine, or tangent, to find the unknown side or the unknown angle, because you've been shown how to do both of these kinds of questions. One thing to note is that you'll encounter problems that talk about the angle of elevation and depression. So some problems involve ideas. The ideas of angle of elevation and angle of depression, you've probably used those ideas before without being formally told what those terms mean. So when an object is higher than an observer, the angle from the horizontal up, from the observer up towards the object, is known as the angle of elevation. So if you're the observer here, this is the horizontal line, that's the horizontal in front of you, and if you're looking at an object that's higher than you, or the observer is looking at an object higher than itself, then it has an angle of elevation up from the horizontal to the object. When an object is lower than an observer, the angle from the horizontal down to the object is the angle of depression. So if you've got the observer here, the horizontal is directly in front. If the object is lower than the observer, then there will be an angle of depression down from the horizontal to the object. The other thing to note is if you've got an angle of elevation from an observer to an object, that's actually going to be equal to the angle of depression the other way around, so from the object down to the observer. So if an observer is looking up towards an object, there's going to be an angle of elevation towards that. But then if you're looking from the object's perspective down towards the observer, the angle of depression from the object to the observer is going to be the same as the angle of elevation from the observer to the object. So I can sum that up with this diagram here. Here's the observer, he's looking up at an object, so there's an angle of elevation. Let's call it theta. Now if you thought from the perspective of the object, there's got a horizontal there, and it's looking down towards the observer, that theta, that angle of depression, is going to be the same. These two will be equal. So you may need to use that property at some point in your calculations. Alright, so let's do an example here. Example, a whale is observed from an 80-meter cliff above sea level at 6-degree angle of depression. Find the direct distance from the observer at the top of the cliff to the whale. So, like in my tips above, you need to find where the triangle is. So most obviously the triangle is here. The cliff is 80 meters high. That would form a right angle with the sea, and this would be the hypotenuse, and that is what we're trying to find, the hypotenuse, the direct distance from the observer, which is at the top of the cliff down to the whale. Obviously this is not to scale, this is over 45 degrees, this is nowhere near 6 degrees, but I need to be able to fit it on the page. So if I use this triangle here, I can't use this 6 degrees straight away. I need to work out what angle this is, which would be 90 degrees takes 6. But I want to work smart, and I notice that there's another right angle triangle here that involves the angle that I already know. If I was to draw this triangle, there's another right angle triangle here. This side would also be 80 meters. We don't know what this side is, and the thing that we're trying to find, the direct distance, is the hypotenuse here. So we can jump the gun, and instead of doing a step to work out this angle, we can just use that 6 degrees straight away. So theta is 6 degrees, so 80 meters is opposite. This is the hypotenuse, which we're trying to work out, and this is the adjacent. I should be working out in blue. So it's a side finding problem. so we don't need to use inverse sine, cos, or tan, but we do need to work out which trigonometric ratio is involved. So, toa. So we need to work out what the hypotenuse is, and we know the opposite. So we need a ratio that involves those. Opposite and hypotenuse is going to be sine. So sine of the known angle, 6 degrees, is equal to opposite over hypotenuse, so 80 over hypotenuse. I need to get hypotenuse by itself. I can't have it just dividing by hypotenuse here, so we need to times both sides by hypotenuse. Times by hypotenuse, that cancels, so you've got hypotenuse sine 6 degrees is equal to 80. I still need hypotenuse by itself, so the opposite of timesing by sine 6 degrees is dividing by sine 6 degrees. So divide both sides by sine 6 degrees, those cancel, so hypotenuse is going to be 80 divided by sine of 6. So grab the calculator because I don't know what sine 6 is in my head. So 80 divided by sine of 6. Make sure that you're in degrees mode on your calculator. And hypotenuse comes to 765.3418 to 4 decimal points, and because the height of the cliff was given in meters, this would be meters. So that is an example of using 765.3418 meters. That's an example of using trigonometric ratios and trigonometry in a problem-solving capacity, and also an example of angle of depression, angle of elevation type of question. Hopefully that helps you out, and I will see you in the next video.